Have you ever stopped to think about what's happening all around us right now? I mean, there's this invisible storm of information just flying through the air. Your texts, your emails, your videos, it's all just there. So today, we're going to pull back the curtain on that everyday magic and take a look at the secret language that makes it all work.
I mean, think about it. You type hi, two little letters, you hit send, and poof, it's gone. Across the room, across the country, in basically an instant. It's obviously not traveling as tiny little letters floating in the air. So what does it actually look like? What's really moving from your phone to theirs? Well, the answer is probably something you've already seen, maybe even something you're studying right now. It's not some kind of sci-fi tech, it's just high school math. Yep, trigonometry and calculus. The same stuff you use to figure out the height of a building or the area under a curve is literally the engine that powers our entire wireless world. All right, so here's our game plan. First, we'll cover the basic and visible language. Then we'll check out a super cool digital lab. We'll get into how we flip waves to talk, create these constellations of data, use calculus to decode it all, and finally, bring it back to the math living in your pocket. Okay, first things first, we've got a fundamental problem to solve. How do you take something digital, just code on your phone, and turn it into a physical thing that can actually travel through the air? Well, here's the secret. Every single thing on your phone, every photo, every video, every character you type is just a long, long string of ones and zeros, binary code. So to send that wirelessly, we have to translate that code into something physical. We have to make those numbers ride on a wave. Now, I know this all sounds super abstract, so to make it real, we're going to look at it through a really amazing tool. It's called the Wi-Fi Lab, and it was developed by a fantastic high school trig and calculus teacher, Kimberly Beecham, specifically to show her students how all this invisible magic actually works. And here it is. This is the lab. What's so cool is that this isn't some complex simulation. It's a website that takes these really high-frequency radio concepts and brings them down to audio frequencies. It literally uses your computer's microphone to let you see and hear digital data being sent and received. And you can see what the goal is here. It's designed to connect the math that students are learning on their calculators, their TI-84s, directly to the phone in their pocket. They can see the waves, visualize the data, and even use calculus to decode a real message. It just makes it all click. All right, let's start with the basics. What is the absolute most simple way you could use a wave to represent a 1 or a 0? It's a method with a kind of complicated sounding name, binary phase shift keying, or BPSK. But don't let the name fool you. The idea behind it is incredibly simple. It all comes down to changing the phase of a sine wave, which is really just a fancy way of saying we're going to flip it upside down. Check this out. It's so elegant. To send a 1, the transmitter sends out a totally normal sine wave. But to send a 0, it sends out the exact same wave, just inverted, flipped completely upside down. That's it. That's the whole trick. You're sending binary data just by flipping a wave. This is a direct application of that unit circle from trig class.
But hold on, where does the calculus come in? Well, look at that exact spot where the wave flips from a 1 to a 0. You get this sharp point, this little kink. A smooth wave has a nice smooth slope, but at that kink, the slope changes instantly. And in the language of calculus, that sudden, jarring change is a huge red flag. It's a signal to the receiver that says, hey, pay attention, new information just arrived.
Okay, so flipping a wave back and forth is cool, but it's slow. You're only sending one bit at a time. You're not going to be streaming your favorite show that way. So how in the world do our devices send so much data so incredibly fast? Well, we get smarter. Instead of sending one bit at a time, we start grouping them together, like say 2 at a time. Then we take that group of bits and we map it to a single point on a graph. And each of those points on the graph corresponds to one very specific, unique wave shape with its own angle and its own strength. And if we pop back over to our Wi-Fi lab, that's exactly what this constellation diagram is showing us. Each of those dots represents a different combination of bits. So now the receiver's job is just to figure out which star in the constellation was sent, and bam, it gets 2 bits of information in the same amount of time it used to do at 1.
And we don't have to stop there. Why settle for just 4 points? So far, we've only been changing the angle of the wave. What if we also change its strength, or its amplitude? That's the distance from the center of the graph.
By using both, we can create way more complex constellations. Something like 16 QAM uses 16 different points. That means you're sending 4 bits of data at once. That is a huge increase in speed.
So we've sent this super complex wave out into the air. But, the real world is messy. The signal bounces off walls, it gets weaker, other signals interfere with it. What the receiver gets is, well, it's not pretty. How does it make any sense of that garbled mess?
And this is really the hardest part of the whole thing. The wave that arrives is never perfect. It's always noisy. So how does your phone look at that distorted, messy signal and decide with absolute certainty, yep, that was a 1, or nope, that was a 0? Is it just taking its best guess?
No guessing. Not at all. The process is called demodulation, and it is a mathematical certainty. It's the job of decoding the message. And the tool for the job is the other side of the calculus coin. We use derivatives to spot the change. Now we're going to use integrals to read the message.
And I'm telling you, this is the absolute killer app for integral calculus. You know all those problems in your textbook about finding the area under a curve? This is why they matter. This is it in the real world. Your Wi-Fi router is doing that calculation millions of times a second to decode messages.
The process itself is just beautiful. Here's how it works. First, the receiver grabs that messy, noisy wave from the air. Second, it multiplies that messy wave by a perfect, clean wave that it was expecting to get. Third, and this is the magic part, it calculates the integral. It finds the total area under that new combined curve. And fourth, the decision. If the total area is a positive number, it had to be a 1. If the total area is negative, it had to be a 0. It's not a guess, it's a mathematical proof that just slices right through all the noise.
Okay, let's bring this all home. We've seen it in the lab, now let's connect it all back to that little supercomputer you carry around with you every single day. So when you boil it all down, it's this beautiful partnership. Trigonometry encodes the message. It gives us the language of sine waves, phases, and amplitudes to turn our 1s and 0s into a physical signal. Then calculus decodes it. Integration gives us that rock-solid mathematical method to pull the original message back out of that signal. And this whole elegant dance is happening constantly at mind-boggling speeds all around us.
Kind of makes you wonder, doesn't it? If the simple act of sending a text is built on such a deep and elegant mathematical foundation, what other invisible languages are out there shaping our world in ways we don't even see? What else is just waiting for us to find the right equation to understand it?